All right. So for the project that's due very soon, you're going to get your own data. So we're between here and here. I'm walking, sure. So basically, when you're going to do it, you're going to get a larger range of frequencies. So what you can do is zoom in, and then we can basically find this point right here. Please, is there not a point right there? There's our point. So this is the frequency in hertz. So we're walking around 1.5 hertz, which should be in general region. And then you can go into your relative magnitude and power. And so where do we care about this? So the area of interest is in this region right here. So what's best? So the yellow one is best. And so yellow corresponds to this last one here. So what we had here, I just made up numbers, but we had two different masses. So it's a bigger mass, and then, what do you mean? Like K?
Yeah.
I didn't look in the chart to see if you can actually buy this spring. I just, 246, 246. So you have to actually look at the chart, and you also pick a mass. I don't know if this is the best mass. I just, and so now 6 is the best. So then we can copy this all over. So now we want to use this mass. And then we want to use, say, 6. Well, maybe we could do 8. I don't know. I'm just making up numbers. So now we want to do it around this, and then we assumed a xi of 0.3. So what happens if we do a xi of 0.2, 0.4, 0.2, 0.3, 0.4? Now we have a different range. So now what we have is what blue is maybe best. So blue because of the resonance, blue has got a peak right here, and then it drops off at higher frequencies, where like green goes up more quickly, otherwise gray. So maybe going up was probably bad. So if we make this, I don't know, back to 4, that's a 7, not a 4. So now, I don't know. So you can decide which of these is better. Again, you're trying to optimize for everything, which means there's trade-offs. So light blue is better here, but lower at higher frequencies, where purple isn't quite as good right here, but when you're walking faster, it's better. So I don't know. This is what you need to think about and discuss why you picked what makes a good combination. And then you should be able to run it, and it will tell you what your power is, and then your relative amplitude. Looks like it's for whatever I have in here is about 4 centimeters, because That's metric system, and math is a lot easier in metric system. 4 centimeters is what, a 2.5, so it's almost 2 inches. Is it going clunk? I don't know. So that's where your range of motion, you need to see, is it going clunk with this? If it's going clunk, you might want to, how can you make it go less clunk?
Stiffer spring.
Stiffer spring or less mass or a longer travel or more damping. Right, so more damping will make your oscillations be less as well, and more damping will also give you more power out as well. So that what you might find out is that this resonant, because this has a much higher amplitude, it might be causing you to go clunk. And so if you reduce the amplitude, you reduce this peak, but then you also, so then you're down here for your amplitude, but then you're getting more power at higher frequencies. So hopefully all that can come together into a reasonable discussion. So that's basically it for the test. It wasn't too pretty. So maximum was 98, which was pretty, but there's definitely a great variety of grades. If everybody does the text corrections, everybody gets 40% of the points they lost, then it almost looks normal, which is somewhat expected, right? So then now the standard deviation does make some meaningful thing, and so the whatever, it's quite a big standard deviation. So at least most people are passing if they do the correction. So there's hope. I don't want to see you I mean, I like you, but I don't want to see you in a year. So that's what we have there. So yeah, all the grading was done on Gradescope. So that's where all the comments are. Gradescope is nice that you say that this mistake is worth 2 points, and then later on you decide it was only 1 point, then it will change it on everybody's test. So it makes it very easy to change your mind if I'm a little too hard or something like that, and then make sure everybody's equal. So this is last year's final, and it's on the Blackboard. It's under lectures. At the bottom of the lectures is last year's final. So again, this final, the final review will go away when the actual final is passed out or whatever, distributed. I guess I'm not going to pass it out because it's all virtual. And so first questions were the warm fuzzy questions. And then there were some mathematical type questions as well. Natural frequency. What's natural frequency? So root K over M. And what does that mean in real life? Yeah, you can put that. You won't get full credit, but you'll get partial credit. Because you want to define or explain. So what is a natural frequency?
The frequency which the system oscillates if it gets disturbed.
Almost. That's -1.
What's the keywords?
So what's omega n? Start at K over M. What's not in that formula? Damping. So it's the frequency a system will oscillate at if it gets disturbed if there is no damping. If there is damping, then it oscillates at omega D, not omega n. So the key word that I pick off 1 point every year, and hopefully I won't have to do it this year, is the frequency that oscillates if there is no damping. Modal analysis. That one we haven't been talking about for very long. That was what we were doing last class. So we take a multiple degree of freedom system, and then we do some math magic on it to decouple the system. So what you're doing is your n degree of freedom system becomes n 1 degree of freedom systems. And so we can basically analyze a multiple degree of freedom system like several single degree of freedom systems. Yeah.
And so if we could analyze multiple degree systems, like a single degree system, is that all you want?
That's probably close enough. But if you're using his words, then you're not using your own words. So only Alec can use those words.
All right, I'll try to.
So yeah, the concept is you're analyzing a multiple degree of freedom system, doing the math to decouple the system. So decouple is probably another keyword that should be in there, which means you can separate the answers. Mode shape. What's a mode shape? Remember in mode shapes where they're going like this or they're going like this? So mode shape is your relative amplitudes on your mass. So relative is a keyword, and that's what's your relative amplitudes, not the amplitude. So whenever mass goes 2, mass 2 goes 2, mass 1 goes 1. So it's always a relative amplitude, which can be scaled. Free vibration?
Not forced.
What's forced?
As a
All right, so now we've got it in a circle. So free vibration is?
vibration without any external forces.
So due to vibration without any external forces, so what does it do to? What? Base motion would be an external force. Chapter 2 is free vibration.
Initial condition.
That's based on your initial conditions. So free vibration is vibration based on your initial conditions. Force vibration is based on some external force. So either base motion, rotating imbalance, some force. Those are, I guess, are 3 ways of getting forces into the system. So force vibration is vibration caused by an external force. Free vibration is your transient or vibration based on your initial conditions. Your total response would be adding your free vibration to your force vibration. Degrees of freedom? Lots of freedom, free. You're sort of on the right track. So degrees of how many independent ways it can move. So 3 masses, if we're talking about a plane, has 3 degrees of freedom. So it's basically the number of coordinates to just completely describe the system. So it's again, what's the word? So it's independent coordinates. So it's a number of coordinates needed to describe the motion. And then this was a warm fuzzy feeling question about chapter 9. And so basically what we have here is a rotating imbalance. And then we have basically a mass, a spring, a mass, and then a spring. So it's 2 degrees of freedom. And then in the second mode shape, at higher frequencies, it had larger amplitude. Why would we have larger amplitude at higher frequencies? Well, what's our input force? Rotating imbalance. What's the force from a rotating imbalance? M times E times omega squared. So why do we get more vibrations at higher frequency? Omega, the higher frequency, so the input force is a lot more at higher frequencies than lower frequency. This was just general concepts, warm fuzzy type equations. And then, so that was too far. So we're going to go backwards through the test because we're going to force through the test. So I wanted to talk about the first question with everybody, going back through the test so that the other lecture went forward through the test. And so between the two lectures, we'll have the whole test. And that will make you happy. And I realized I did this problem wrong when I did it in my office. So we'll have to do some calculations in real time. Most of it. All right, so what do we have? Orthogonality. So 2 by 2 matrix. What do we do 2 by 2 matrix? Math is easier, yeah. So orthogonality is basically x1 transpose times m times x2. That's equal to 0. That's orthogonality. So that's the definition. And so what do we have? We have 1 minus 3 times 6004 times 1r2 is equal to 0. And so multiplying it through, we have 6 minus 3 times 4 is 12r2 equals 0. So therefore r2 is equal to 1/2. So then your mode shape is going to be 1 and 1/2. So this would be x2. So that's the first mode shape. So orthogonality, x transpose, one mode shape times your mass times your second mode shape is equal to 0. What about B? Normalize. What does normalize mean? Then we have x1 transpose times m times x1. That has to equal 1. So we can apply a scaling factor to each of your x's. Because again, this is a mode shape. This is your relative amplitude. So mass 2 is always going minus 3 times mass 1. So in this case, mass 1 is going to go P1, and mass 2 is going to go minus 3 P1. All right, so this will be P1 squared. And then we have 1 minus 3, 6004. 1 minus 3. So it's P1 squared times, we have 1 times 6 times 1 is 6. And minus 3 times 4 times minus 3, so that'll be a plus. 9 times 4 is 36. So it's P1 times 42. Squared, so therefore, let's do a therefore over here. Therefore, P1 is going to be 1 over square root of 42. Yeah.
Is the superscript 1 in parentheses, is that different than just the subscript?
Yes, it's the same. Thank you. So the book did superscript parentheses. I did subscript. I'm a bad person, or at least forgetful person. So basically, then we have that x1 is 1 over the square root of 42 times 1 and minus 3. All right. Natural frequency. How do you determine the natural frequency based on the normalized mode shape? Well, we have the x1 transpose, which times k times x1, that's equal to your natural frequency squared. So if your equivalent mass is 1, then the equivalent k is your natural frequency squared. So it's 1 over the square root of 42 times 1 minus 3 times our k matrix is 6 minus 4 and 5 times 1 over the square root of 42 times 1 minus 3. So that's equal to, hey, it's a take-home test. We have MATLAB. So what do we have? We have, oops, probably should share our screen. So we have 1 minus 3 times, let's just call this omega n2. So 1 minus 3 times 6 minus 4 minus 4, 5 times 1 semicolon minus 3 divided by 42. How do we, where's the gear? So we're dividing by 42. Why do we divide by 42? We have 1 over square root of 42 and 1 over square root of 42. So rather than squaring that, so this by MATLAB is 1.786. So therefore omega n is the square root of 1.786 equals $1.3 4. All right. How do we get this? Where's settings? Home. Preferences. Command window. Where's your font? It would be helpful if we could change the font. I guess we're stuck. All right, so that's how we can solve for the natural frequency. Part D, so if your natural frequency of the second mode shape is 3.4, system is undamped and starts from rest using your frequency from C and your mode shape from A. What would be the time response equations for initial position? All right, so what's your time response? This was actually on the test. So x1 of t is equal to what was our mode shapes? 1 minus 3. So it'll be a1 cosine of the omega we had was 1.3, what is it, 1.34? Plus a2 cosine, what frequency? 3.4. And then x2 of t is equal to our first mode shape had the second mass was going minus 3 times the first mode shape. The first mass. So for the first mode shape, the second mass is going minus 3 times the first mode shape. The second mode shape, the second mass is going a half times the first mode shape. And so it's plus 1/2 a2 cosine 3.4 t. So x1 of 0 is 1.1, and this is negative 1.5. What's that equal to? Plugging the 0 into here. A1 plus A2 minus 3A1 plus 1/2 A2. So we can write this in matrix form. 1, 1 minus 3, 1/2. So we invert that and multiply it by 1.1 minus 1.5. That gives us A1 and A2. So it was 1, 1 minus 3.5. Inverse lat is a backslash times, it was 1.1 and negative 1.5. So that gives us 0.5. So that is 0.586 and 514. So therefore, x1 of t is 0.586 cosine 1.34 t plus 0.514 cosine 3.4 t. And x2 of t is negative 3 times 0.586 cosine 1.34 t plus 0.5 times 0.514 cosine 3.4 t. So there was a problem similar to this on the second test. But last year there was a problem like this on the second test, so it showed up on the final. Oops. All right. What would be the transient response of the first mode shape? So this is modal analysis. We were analyzing the first mode shape like a 1 degree of freedom system. So what are the equations of motion? Right, so if we can write it as alpha times the identity and beta times your natural frequency, so that is if your damping is alpha times m plus beta times k, then we can use modal analysis, and so the C term or your 2 zeta omega I term is right here. And so looking at our problem, what's alpha and what's beta? Well, here is your damping term. Here's your K term. I'm spelling it out for you. So the 0.3 is beta. So beta is 0.3. So we have beta is 0.3. And so we get 0.3 times omega squared. What's the natural frequency here for our first mode shape? 1.34. Natural frequency squared is 1.786. So beta times omega I squared. So it's 1.786 is equal to 2 times squiggle times 1.34. So this was alpha plus beta omega I squared equals 2 zeta omega I. And so we can what's our zeta? So to get our zeta, it's beta over So beta omega over 2 is zeta. Am I doing the math? The omega is going to cancel. Zeta, so omega is going to cancel with one of these. So beta over, so zeta is equal to beta omega over 2. So it's 0.3 times 1.34 over 2. Any math? So it's 0.3 times 0.3 times omega n divided by 2. So zeta is 0.2. And then how do we get our initial conditions? So our initial position of our mode shape is X transpose times M times the initial condition. And so we have Q0 is our mode shape. Transpose is 1 over the square root of 42. It's going to be normalized times 1 minus 3 times our mass matrix. What was our mass matrix? 6004 times our initial condition, which was 1.1 and negative 1.5. So that's, so this was X1 transpose times M times X 0. So that's 1 over the square root of 42 times, what is this, 6 times 1.1 plus or minus 12 times negative 1.5. What is that? Math? Is it 4? No, 6. 6004 times 3.8. Right, so this is chapter 2. This is the transient response from chapter 2. What's omega d? So omega d is omega n, 1 minus zeta squared. So it's 1.4 times the square root of 1 minus 0.2 squared. Omega n times 1 minus zeta 1.3. So the frequency it oscillates with damping is omega d. So then this becomes e to the minus 0.2 times omega n was 1.34 times our Q0 is 3.8, so it'll be 3.8 cosine of 1.3t plus x naught 0 is 0, so it'll be 0.2 times omega n is 1.3 times x0 is our Q0, 3.8 over, omega n. Oh, this is 1.34 over 1.34 times sine of 1.3. So we basically use beta so that we can find our zeta. And then we found our initial condition by x transpose times m times your initial condition. And then we basically have a chapter 2 problem that we can solve. All right. What about forced response? So how do we do modal analysis for forced response? So our input force is 1.2 sine of 3.4 t. So looking at your modal analysis, your decoupled force is going to be your x transpose times the input force to the system. So our input is x transpose times your force. So our X transpose was 1 over the square root of 42 times 1 minus 3 times our input force, 0 minus 1, that's this. And then our actual force is 1.2 sine of 3.4 t. So that's equal to 1 minus 3 over the square root of 42 times 1.2.
Professor?
Yeah.
Why is it minus 1?
Because I'm wrong. I'm trying to copy what's right here over to right there. I got excited by this minus, and so because that, this becomes negative. So then 3 divided by the square root of 42 times 1.2. 555. Another 5? Oh, that's okay. All right, so that's our input force. What's the forced response? Amplitude of the forced response, X we had was F over delta static, and then it's 1 minus omega over omega n squared plus 2 zeta omega n squared, the square root. So plugging into our virtual world, our force is 5555. So it's actually, it's F over K. So 0.5555 divided by our K. What do we have for K in the system? So your K is going to be your omega squared. So that was 1.7, right? 1.76. So K becomes omega squared over 1 minus your omega is 3.4 over 1.34. So your natural frequency was 1.34. Squared plus 2, our zeta was 0.2. And then this was not omega, this was omega over omega n. So it's 3.4 over 1.34 squared, the square root. So basically what we've done is transferred a multiple degree of freedom problem. We found the forced amplitude And then we use our corresponding equation over here. We also could have probably used F over K minus M omega squared plus C omega squared, the square root. And your C is your 2 zeta omega n, which we learned in controls. But question?
I was gonna say that could work too.
What?
So that one could also work.
This one will also work.